In this video, we're going to talk about graphs and graph models. So we have a lot of vocabulary in this section, and I'm going to kind of jump through it and leave you to kind of read and go through that. But graphs, which we typically label G equaling VE, where V is representing the number of vertices, also called nodes, and E is representing the number of edges. Each edge has either one or two vertices associated to it, and they're called endpoints. And an edge is said to connect its endpoints. So let me draw an example of a graph with 4 vertices and 5 edges. By the way, we would label that G of 4 comma 5 based on the notation that this author has introduced. And here, if I want 4 vertices, and I'm going to give them labels, so that'll be A, B, C, D, and I'm going to connect A to B, B to C, C to D, but how about I'll keep it exciting, and rather than connect A and D, I'll do D to B, and how about A to C? There we go. That's 5 edges connecting those 4 vertices. And of course, there are options for me to make other connections, but this would be an example of this kind of graph. Now, we have a lot of freedom with how we draw these. In fact, it kind of depends even on which textbook you use, how they describe the terminology with the graphs. So there's definitely some varying in the terminology, but they do basically refer to these same basic kind of images that show connections. Okay, so a graph of an infinite vertex set is called an infinite graph. So it is possible to have like infinite bouncing back and forth. We won't really deal with those. We're going to just look at finite graphs. That's what we'll be kind of focusing on. And then this next definition is kind of an important one. A simple graph is a graph where each edge connects 2 different vertices and no 2 edges connect the same pair of vertices. So what we have up here, this is definitely an example of a simple graph, because what we're depicting is that A and B are only connected with one edge. There aren't multiple ways to connect A and B. If there are multiple ways to connect them, that would be called a multigraph. And a multigraph has multiple edges connecting them. We do give labels, and we call the multiple connections, we actually call those multiplicities. It is possible for a vertex to just connect to itself with an edge. They call that a loop. And then a pseudograph may have many loops and as well as multiple edges connecting the same pair of vertices. So here, let's draw an example of a pseudograph. I'm going to only do 3 vertices this time. Here, I'm going to kind of put that off to the side. All right, so let's say A and B are connected, B and C are connected, and let's say A and C are also connected, but let's also say there's an additional connection between A and C and additional connection between B and C. And let's say there's even a loop that connects C to itself. There you go. That's a pseudograph. Multiple connections and loops even onto a vertex for itself. All right. And again, just to kind of emphasize the language they use in this one, we'd have 1, 2, 3, 4, 5, 6 vertices, but I'm sorry, we have 3 vertices, 3 vertices, but 6 edges. There we go. So first one is vertices, second one is edges. All right, just so we can kind of use that terminology. Okay, a directed graph means we actually indicate direction. This is particularly useful when we start looking at some examples later on, like network connections and whatnot. But we call those directed graphs. Some places call it digraphs. And the directed edges could be called arcs. And we often emphasize the order of connection going from U to V with this ordered pair notation that we have used previously. All right. Graphs where the endpoints of the edge are not ordered are said to be undirected graphs. Okay, let's look at an example of that in just a second. Sorry, we have some more terminology. So a simple directed graph has no loops, no multiple edges. A directed multigraph could have multiple loops and edges. And then, of course, we can talk about multiplicity again in that case. Okay, so here, let's do an example of a simple directed graph with 3 vertices, 3 edges. So like a very simplistic graph. Okay, so here's A, B, C. I'll just keep them in the triangle formation here. So, oops, so sad. Try that again. A goes to B, and then let's indicate it goes like that. So we'll use the little arrow to indicate that that's the direction it goes. B goes to C, and then let's say C goes back up to A. And there we go. That would be a simple directed graph. Okay, so let's do a graph, a directed multigraph. This time we'll have a multiplicity for AB to be 1 and from BC to be 2. Okay, so here, let's do that. So same kind of basic shape, A and B. And then let's say here's C. And okay, so A to B is only 1, so I'll keep the same direction from A to B. But for B to C, they want 2. So often we use curved lines. We don't have to. We can use a straight line and a curved line. Just kind of depends on how you feel like drawing it. They didn't tell us anything about A to C, so hey, I could do a double connection there as well. Why not? So let's say it goes like this and then like this. And if I really wanted to, I could also throw some loops in here. So like here, I'll put a loop there on B, and I should give a direction too, just so that it has direction. So there you go. There's a directed multigraph that displays a multiplicity of 1 between A and B and a multiplicity of 2 between B and C. But it also displays a multiplicity of 2 from A to C as well. And then we have some loops that we went ahead and threw in there for the fun of it. Okay, so let's look at some models. So this is specific examples that we'd be using graphs for. Computer networks. All right, so this would be a graph of a computer network showing the connections between the different cities. In this particular graph style, based on our terminology, this would be considered a simple graph. Since they don't have any sort of direction, they don't have multi-edges. We're going to see what that looks like in a minute. We're going to add to this graph, okay? But this would be how a simple graph of computer networks would look. We are representing data centers and then communication links. It's possible that we're wanting to look at some more complicated versions of the graph. So here I kind of went to the next page and I decided I would add in the complicated versions. And here I'm going to use my black pen to do that. So let's say we want to do a multi-graph. So in this case, let's go ahead and connect additional connection between Los Angeles and Denver. Let's say there's actually 3 connections between Denver and Chicago. Let's say we have an extra connection between New York and Washington. And let's say we have another connection between Chicago and New York. All right, so that would be a multi-graph connection between the computer networks. Let's look at diagnostic links. So in this case, we're going to need pseudograph to do this. So we'll still have all of the multi-graph edges. So let me throw those all in. But we're going to throw in, oops, sorry, let me do a better job on that one. There we go. We're going to throw in the fact that we want them to be able to do diagnostic links at the data center. So those require loops. Now, I didn't really give myself much space, so I'll put a little loop there. Washington will have a loop there. Ooh, Detroit's tough. Here, I'll make a big loop. Why not? Chicago up above. Well, here we'll do Denver up here. San Francisco off to the side. Same with Los Angeles. So there we go. Having those diagnostic links will add the loops and turn it into a pseudo graph. Okay, or maybe we want a directed graph where there's actual edges that send data from one center to another. Okay, so let's say I come back in here and from Denver to Chicago, let's say I go this direction, and then let's say that existing line goes this way. But what if there's another pathway that does it? So here, let me do that. Let's say there's another one that goes this way and another one that goes that way. All right. Okay, here, let's connect Chicago and Washington, and then let's go ahead and put an additional link going back the other direction. Let's go one way here, the other way there. Let's go. Oh, here, let's do, I'm going to try to squeeze this one in. Ooh, that was rough. Let me decrease the size of that one and move it a little bit. Okay. So here, let's say these, I just can't seem to get myself enough space. There. Okay. Let's say that on this connection, it goes from New York back to Chicago. And then let's say we have a connection between Chicago and New York that go one way. But let's say Detroit's kind of special. Let's just say it's got two connections that kind of work like that. No multi-loops there or multiple edges there. Okay, here, let's come back over here to Los Angeles. Let's say these two are connected. Wow, that's a terrible arrow. These two are connected. And then let's say there's one going backward. Let's say there's a connection between San Francisco and Denver. But let's say there's other links both ways, go in the other direction from San Francisco to Denver. Let's say we have these two connected and these two. Okay, oops. Let me give myself a little bit more space. And there you go. Whew. Directed graph with multiple edges shooting between the connections of the networks. All right, and the data centers. So that's how we can use graphs to depict these connections, including directions, diagnostic links, all of that. All right, so to understand the structure of a graph, we need to kind of ask ourselves, are the edges directed or undirected or possibly both? If they're undirected, are there multiple edges that present this that connect the same pair of vertices? If the edges are directed, are multiple directed edges present? Are there loops? And those questions lead us to different labels for the graphs. So here we go. This would be the types of things that can exist for the graphs. When we have undirected edges, that means we're typically talking about a simple graph, a multigraph, or a pseudograph. All of those can just have undirected edges. Are multiple edges allowed? Not in the simple graph, but in the other two, yes. And are loops allowed? Only in the pseudograph. In fact, I think up here, I may have thrown in a loop on something that wasn't considered a pseudograph. I'm going to scroll back to it. Right here. This said it was a directed multigraph. So here, I'm going to throw this loop off. In fact, that was given in the, not the textbook, but in a lecture note thing I was looking at. So sorry about that. That shouldn't have had a loop. Because that makes it a pseudograph. So we'll make that fix. Okay. We can't have a simple directed graph. That's possible. No multiple edges, no loops. A directed graph. Yes, that's possible. We can have, we could have a loop. I didn't need to erase that loop. What a dork. Okay, that's all right. I didn't get down to there yet. And then a mixed graph can have both directed edges, undirected edges, loops. It's kind of mayhem. All right. Sorry, I can't believe I didn't bother reading even further to make sure I'd done that correctly. Okay, another example, social networks. All right, social networks. And man, with social media, that really does change the way social networks kind of work and look. So here, there are what we call friendship graphs. So friendship graphs are undirected graphs. I'm going to zoom in a little just so I'm not doing a sloppy job. Undirected graphs where two people are connected. If they're friends. And then, of course, how they became friends might vary. Perhaps they're friends in real life. I'm going to use IRL to represent that. I think most of us are familiar with that. Maybe they're friends on like Facebook or Instagram or TikTok. Or maybe they're friends virtually, like through a game. All right. There's lots of ways to have friends. It doesn't have to always be in real life or through social media. Okay. Here, let's draw an example of a friend graph. So here, I'll do this in green. All right, here, I'm gonna throw some names. We'll make this Jan, Pam, Paul, Jose, Glenn, Chin. We'll throw Flo in there. How about Frank? And then how about Paula? All right, there we go. So let's say they're connected like this. I'm just going to throw some connections in there. So let's say Frank is friends with like a bunch of people. He's a friendly guy. All right. Oops. All right. And then let's say Paula is very tight with Paul because, hey, they have similarity in their names. Let's say Paul is connected to Jose and Glenn. Let's say Glenn is friends with Chin, and so is Paul. They're all pals. Let's say Chin is also friends with Pam. Let's say Pam is very social. So let's say she's friends with Paul and Jan as well as Frank. All right. And then, hey, maybe she's also friends with Flo. Flo's kind of more to herself, and so is Paula. But there you go. You get the idea. Not as to themselves as Jose is over here. He's kind of, well, here, let's give him some more friends. Let's say Jose is friends with Chin. Oops. Kind of drew that badly. And Glenn, why not? He's making friends now. And there you go. There's an example of a friendship graph. Okay. Collaboration graphs. So this is more when we're talking about collaboration, not so much friendship. So again, it's an undirected graph. Where two people are connected if they have collaborated. Examples of that could be like maybe you guys worked on a school project together in a class, or maybe you had a class together. That's a good one. One that the book kind of takes some time to discuss is like a Hollywood graph, where actors are connected based on the fact that they have been in movies together. Actors, and that when I say actors, I mean actors and actresses are connected through, wow, that's not how you spell through, are connected through movies done together. And it's possible for two actors to act in the same movie and actually not meet each other. That doesn't mean they're not connected. It just means they haven't really met necessarily. That's a possibility. All right. Okay, influence graphs. So now this is the first time we have directed graphs. So a directed graph, and the way there's direction in these kind of social environments is when somebody actually can influence another person. So it's a directed graph where one edge, oh, wow, I forgot to say graph. Directed graph where one edge between two people represents the first person's influence, the first person's ability to influence the second person. Now, influence graphs typically are more in person, right? People you meet that have an influence on you, teachers, students that you've, worked or collaborated with, and you find, oh, hey, they're a smart person. I like to listen to what they say. Friends, of course, family, your aunt, uncle, I don't know, people you have connections with. But of course, we're very well aware that nowadays there are influencers online, people who inspire, or give advice to, and people listen. So let's say Dan, let's say he is influenced by both Mike and Jorge. Oops. Let's say Jorge also influences Mike. And then let's say Mike influences Rosa. Ooh, but let's say Rosa also influences Mike. They influence each other. Let's say Pat influences Mike. Let's say Rosa influences Pat. And then let's say Jorge influences Pat. And there you go. There's a connection. People being influenced, helping influence. There's our influence graphs. All right. So now we're going to kind of get into just some more examples without so much of me drawing the graphs. These are going to be more given to us because they're kind of getting complicated and it's taking a lot of time to draw them. So software design. Graph models are extensively used in software design. So we have two versions we're going to kind of look at. One is representing the dependency between the modules of a software application, and the other representing restrictions in the execution of statements in computer programs. Okay, so when a top-down approach is used to design software, the system is divided into modules, each performing a specific task. So we use a module dependency graph to represent the dependency between these modules. Let's look at what that might kind of look like. Here's an example of it. So we have the main system, which speaks to the parser and the protocol and the display and the abstract syntax tree and page and network, and you kind of see all the connections between them. So there's an example of a module dependency graph. We also have a precedence graph. And a precedence graph represents statements that have already been executed before we execute each statement. So vertices represent statements in a computer program. There are directed edges from vertex to a second vertex if the second vertex cannot be executed before the first. And here is a drawn out example of this. As you can see, it can get very complicated. We have lots of the labels set up, and of course, it is directed. Okay. Let's look at biological applications. Niche overlap graphs model competition between species in an ecosystem. All right. So some animals are competing with each other for food, water, shelter, all that fun stuff. So this would be an example of where we'd see that. Maybe a hawk and a crow are competing. A squirrel is probably competing with certain birds, as well as other animals similar to it that live in trees and those kind of areas and so forth. All right. We can also have an interaction of proteins in a cell. That's a protein interaction network. These can get, as you can see, very complicated. Whew. Showing the protein interaction of graphs of proteins that degrade the RNA in a human cell. And then there are some other graphs that the book does mention, in information graphs and transportation graphs, like if you're studying a city for planning. Information graphs is actually something they hit on in a different section. But there you go. Introduction to graphs.